stations. So, thank you very much for the introduction. And I would like to dedicate this presentation to Louis Dumont, who died a few months ago after severe but short illness, and who had been looking forward to this presentation already. So this first presentation looked at big power stations. I will look at small and medium-sized power stations and the barriers there. Nevertheless, I would like to mention that this is just an overview. We looked at different procedures and methods used for upwards and downwards migration of fish. We have fish locks, bypasses, fish transport systems, and in bigger hydropower stations there can only also be fish-friendly turbines, fish management and so on, which is not such a valid solution for smaller hydropower stations. Now the fish protection facilities for smaller hydroelectric power stations, there I want to focus on barriers, behavioral barriers mainly, through optical acoustic methods. They try to hinder fish from entering certain facilities. And we know that at the moment they cannot efficiently be used, and this is why we currently focus on mechanical solutions for smaller hydroelectric power stations and then scale them up or down to the to work for the individual power stations. This is the case for the protection of diatromous fish, for instance, 10 millimeter distances for salmon smolts. And here the phase velocity is reduced to less than 0.5 meters per second. Overall, our objectives in this field are that we choose width of the bars that physically hinder fish from passing. Then we need to choose the right phase velocity. Here I wrote vectors because we have to consider what directions the flow goes to, and when we have behavioral barriers there, it can be that the phase velocity is smaller than the fish swimming capacity. On the other hand, it is also possible if we have high velocities and work with a high tangential vector along the channel and then cause a passive drifting of the fish. But anyway, we need to take into account the specific behavior of the species, define these beforehand, and here it is important that the entire unit of bypass and barrier is designed in a way that the surface is adapted so that fish is not damaged when they migrate. So we learn about the behavior of fish at mechanical barriers in the lab through lab experiments, which mainly focus on smolts and eels. I must admit that regarding other fish we do not have so much data yet, but there is research ongoing. And since regarding the fish protection schemes for smaller hydroelectric power stations, we usually upgrade existing facilities. There we need to know that it's usually 15 to 15 millimeters, and bigger ones 50 to 100 millimeters distance of the bars. And also there are differences in phase velocity, 0.4 to 0.8 millimeters per second for smaller hydroelectric power stations. If you have a bigger facility, they can be significantly higher. And the incline of the screens and rakes are also different. In small facilities they are flatter, and in bigger facilities they are more inclined. And these are usually the preconditions we need to take into account in the individual locations, and then we need to find a technical solution and choose the right procedure. Basically, we use two different designs for smaller hydroelectric power stations. Mechanical barriers with a guidance effect, and which are directly linked to a bypass. And there we have the overflowed barrier, where the fine screen has only a small slope, and we have a tangential flow component towards the bypass. So the bypass is lying on the top, and at the same time makes sure that floating matter and the fish are transported into the right direction. A second version here, there we have a vertical screen with horizontal bars placed in the flow direction with a certain slope put into the channel. And at the end of the screen we have a volume, and there the bypass channel is placed, and then we have a closing gate, can be a swiveling gate or another gate, and this controls the flow there. One very important point with regard to the design of fish protection facilities is to look at the flow situation in the of the incoming flow. This is part of a 2D calculation, and this illustrates how the small arrows showing the direction of the flow and the strength of the flow, this shows the behavior, and this analysis gives us or indicates whether the parameters chosen are the right ones to make the bypass attractive to fish or not. We are trying to take into account the tangential component here, keep it constant. The normal of the velocity should not be too high. We have 0.3 to 0.4 meters per second, which we do not want to exceed. And in total, the ratio between the water let into the bypass to the water flowing through the turbines must also be taken into account. And one example here for one facility using this design. This is a small hydroelectric power station at the river Wupper in Germany. We have a discharge of 16 cubic meters per second. And here we wanted to protect salmon smolts. Have a have a screen here with 12 millimeter bar distance, and then we have certain gates making possible that the fish is let into a bypass. And we have a flap up there controlling the flow. Before this was put into practice, a lot was discussed: where will the fish swim, where's the right location for the bypass. And this is one of the few procedures that I know where in cooperation with the operator and the authorities, a concept was developed that did not finish after construction, but all the stakeholders said we will do monitoring, we will look at whether adjustments are necessary from hindsight. And this is also how this entire project was designed. Now, regarding the bypass itself, I want to refer your attention to the DWA data sheet, the old one, which is still valid, I think, because it contains good recommendations and principles for insulation, for instance, and I think this is very important. For instance, if we have bypasses close to the surface, there it is recommended that we have one bypass every 10 meters of screen, at least 0.4 meters of water depth, and bypass flow to turbine flow should be 2 to 10%, the ratio here. But this can actually differ depending on the actual situation on site. And what is important here is to avoid turbulences, and we found that having a funnel-shaped design for the inflow is rather a good solution. If we have a bypass channel, then we must make sure these have a smooth surface, and the velocity must not be too high, the velocity within the channel. It is furthermore recommended that the bypass channel is, or the outflow into the tail race is above the water surface. I would like to show you one more picture of this horizontal screen to show you what additional migration ways are offered. We have a high-lying screen there with a channel behind that makes it possible for fish to swim in. We have a 50 centimeter opening close to the surface, close to the gate, and another opening close to the riverbed for the eels. Then we also have a flushing gate that can also be used for downstream movements. And there you see this, the blue arrow was the direct way. And what was interesting here in this project, we had an additional alternative, namely the upwater inflow of the fish ladder. That was also a possibility here. Then the monitoring facilities. These are mainly pools that are planned to be used to count the fish descending. However, the monitoring is actually now done with transponder examination, so that all the many different descending ways are taken into account at weirs, for instance, because we wanted to see how does the migration behavior, downstream migration behavior, work there? What way do the fish choose? Are we really focusing on the right locations? And do they use the entries to the bypasses we are offering or not? And this examination by the Institute for Applied Hydrology are still ongoing. It's a long-term monitoring, and as far as I have seen so far, we have very interesting interim results. Not actually what we expected. we already identified some problems. For instance, this eel tube at the riverbed, there we have constant congestion problems. So regarding the eel downstream migration, we still lack a good and practical solution. Regarding the migration close to the surface, the situation is better. There we find that the fish really use the different ways we offer them, also via the upstream fish ladder and via the rinsing channel. And in addition to this horizontal screen, for small hydroelectric power stations, we also use a different design, the vertically inclined screen at a certain angle to the riverbed. And here you must look at the flows, the different velocities, velocity components, and then you have to design this surface water bypass channel adequately. This kind of fine screen can be easily installed at existing facilities because its design is very close to the conventional cleaning mechanism for the screen. So this is easy to install usually. And we first tried this at a facility close to where our office is. They have a fine, very small width of 5 millimeters and an old conventional chain cleaning device. And since we installed that solution, we've seen rather good results. And against this backdrop, one more point must be considered, namely the different bar profiles that you can use for the screens. There's now a great variety of bar forms and shapes. And I think more is to come in future. There's more under development. Mechanical engineers will offer more solutions here. And in this regard, it is important that the rake or screen profiles are adjusted to the cleaning devices. We have at one facility a profile that is similar to the one used here. This is a hydroelectric power station at the River Ruhr in Germany, at the Dutch border. And here we have a 10 millimeter fine screen with a conventional floating matter channel and a container on the side. And here the bypass was placed on the side and designed in a way that it quickly guides the fish into this section with a small Tyrolean screen, and which then leads on into bypass tubes, and which then flow out or flow into the tail race again. Another example for this design with a vertical fine screen and a bypass channel close to the surface is this hydroelectric power station. we have a bypass on the side, the bypass opening directly over the screen fields on the right and left side, and the pictures show here this is facility still under construction. Later on, after the construction, they had to adjust the fine screens a little to improve the flow. This is now a picture from when it is in operation, and you can see the bypass here with the screen and with the bypass channel lying behind it. Then there is one other variant of this design where only details differ from the previous versions. Here you have the fine screen and the rake. Then we have the bypass channel behind it, and this is used for the outflow of pebbles and so on up to a certain size. They are transported to a conveyor belt and are then conventionally disposed of via a container. And this facility here, there are also form pieces, or form pieces can put into the side to adjust the outflow after the actual construction time. And here we have a bypass close to the surface, going to the weir and then flowing into the tail race of the weir, and here it had the fish then are brought into the tail race together with the bypass water and the floating debris. And here one point needs to be taken into account. But the modern cleaning devices these days are already a good solution here. But we found it must be important that the cleaner for the screen must be adjustable so that it is really effective. We must adjust it to the fish's behavior, because we found that sometimes fish are waiting up in the upper part of the screen. They wait before they enter into the bypass, and if this cleaning device starts at the wrong point of time, this can be counterproductive, but we now have control mechanisms for these screens, and this is no longer a problem now with modern solutions. And generally, in the area of these entry sections into the bypass, you must make sure that the surfaces are smooth, that the water depth is sufficient, and that we have the right flow velocity. I wrote adequate flow velocity here because we still don't have reliable data on what is the right flow velocity, and this is something we will have to take a closer look at in the next few years. So it is clear that certain flow conditions like too high velocities disturb downstream movements, but too low velocities can also disturb the downflow movement, and here we need to find the optimum velocity, and this is some work to be done in the next few years. And this brings me to the outlook. I can only point out again what we heard in the first presentation. The technology I presented here, and which we mainly use, is used for smaller hydroelectric power stations, and we think it can be used up to 30 cubic meters per second per unit for the vertical screen. For the horizontal screen, maybe a little higher even. But we see that we still have knowledge gaps regarding the design of bypass and the long-term behavior of the screens, also with the units combining cleaning mechanism and screen. There we need to do further investigations. The problem is that we haven't had so many of these installations for such a long time yet to have reliable data. And when you design a new facility, you need to take that into account, make sure that you can make adjustments later on after some time of use. So this shows that this technology is not an alternative for large hydroelectric power stations. At the moment, for large hydroelectric power stations, we rather recommend fish-friendly turbines or better runners or different alternatives for bypasses, irrespective of the protection technology you use. Operational management could also be a solution. However, we do not have sufficient information on the behavior of many species of fish yet, so not enough knowledge, not enough data yet. And if you have chains of different facilities, one after the other, then you can also consider barge and truck or trap and truck solutions. Then there is good literature available. I think there are 3 standard works if you want to learn more about this topic. I included the DWAM 509, which Steffenheimer presented yesterday, because a lot of statements are in there that are helpful for fish protection and downstream movement. Then there's the fish protection technologies and downstream fisheries, also from DWA, and in the handbook for manual for transverse structures you also find a lot of information. That was it. Thank you very much for listening to me.